Okay, as we continue our treatment of convergence of infinite series, we will today learn the ratio test. The essence of the ratio test is with a comparison actually to a geometric series. So that will be how we'll understand this. Now, the ratio test, we're coming back to dealing with series where all the terms are non-negative. And actually, it would be better to just say that the terms are positive. So we have a sum of positive terms. And suppose that we have rho, which is the limit of an plus 1 over an. If that limit, the limit of the ratio of successive terms, if that limit rho is smaller than 1, the series converges. If rho is bigger than 1, the series diverges, and if rho is equal to 1, then the test is inconclusive and it doesn't tell you anything. You have to go to a different method. So what's the idea here? Well, the idea is if we focus on this limit, what this says is that for large N, an plus 1 is approximately rho times a sub n. And the larger n gets, the closer and closer this becomes to an equality. Well, what is this? This is saying that the n plus first term is approximately rho times the nth term. So the terms, this looks like the criteria for geometric series. And remember, a geometric series converges if the absolute value of that ratio, rho, is less than 1. Now, it's also true that the terms, the ratio test is only used for a series of positive terms. So by definition, rho has to be greater than or equal to 0. It can't be negative. So what's happening is we have a rho that's greater than or equal to 0 by definition. Right? If an plus 1 and an are both greater than or equal to 0, this ratio can never be negative. So the limit of that ratio would never be negative. So what's happening is this is like having a geometric series where your r term is always greater than or equal to 0. And we're then just, given that extra caveat, we are just borrowing the convergence criteria for a geometric series. So if that rho is less than 1, that's the geometric series case over here, where you get a convergent geometric series. If rho is bigger than or equal to, if rho is bigger than 1, then our series behaves like a divergent geometric series. And then the test is inconclusive if rho equals 1. So that's basically the idea. As you go further and further down the line, the terms in the sum, the terms are looking more and more like terms from a geometric series. So again, that's why this 1 is the cutoff. It comes from that geometric series criteria. Now, how do we use ratio tests? Here's an example. We usually would rewrite this as the sum n equals 1 to infinity of n squared over e to the n. And we remember, always we're answering the same question. Do these terms approach 0 fast enough so that this sum will be finite? Polynomial on the top, exponential on the bottom. We know the exponential races to infinity dramatically faster than the polynomial. So this probably has a chance to converge. These terms may go to 0 quickly enough. So that's our guess. And to show it, we will use the ratio test. So we set up this row right from the theorem. So remember, it's the ratio of the n plus first term to the nth term. And you have to be very careful with your algebra with these questions. It can be very easy to make a mistake if you aren't writing things really carefully. So you always want to be writing things very carefully. So the n plus first term, you get that by going into the summand here and replace every instance of n with n plus 1. So we have n squared, n plus 1 squared over e to the n plus 1. And then for the a sub n term, we can just copy the term as it is. And now we have a Calc 1 problem where we have to simplify and find this limit. So this will be the limit as n goes to infinity. So simplifying, we have n plus 1 squared in the numerator. And then we have e to the n plus 1 in the denominator. And then this n squared will stay in the denominator. But this division by e to the n in the denominator moves the e to the n into the numerator. And we can start to simplify. So this is the limit as n goes to infinity of, we can FOIL out this n plus 1 squared. So that'll be n squared plus 2n plus 1, e to the n. We can then use our rules for exponents to rewrite this as e to the n times e to the 1. We then see that the e to the n terms cancel. This then becomes limit n goes to infinity. E to the 1 in the bottom, that's just a constant. That's just 1 over e. So we can write it as 1 over e. And then we have times n squared plus 2n plus 1 over n squared. And remember, the way that we handle these types of limits is by identifying the dominant term in the denominator and then dividing every term in the denominator and in the numerator by the dominant term from the denominator. So this gives us n squared over n squared plus 2n over n squared plus 1 over n squared over n squared over n squared, or limit n goes to infinity, 1 over e, simplifying, we get 1 plus 2 over n plus 1 over n squared over 1. And then application of our limit laws give us that these terms circled in red approach 0, which gives us a 1 in the numerator and a 1 in the denominator. And so this happens to all approach 1 over e. E is bigger than 1, so this is less than 1. And remember, that was the whole point. This was rho, the ratio of successive terms. And because it is less than 1, this means our series converges by the ratio test. And again, the intuition being, as you go further and further into the terms of this series, each term starts to look closer and closer like the previous term times 1 over e. So this is how you use the ratio test. When you see complicated expressions that have exponentials in the denominator, the ratio test will work. It will often work. Let's do another one. Now this is something that we haven't had much experience with yet, this idea of factorials. And factorials grow really quickly. So let's take a look at how we handle this. And remember, with any series of positive terms, question is, are the terms racing to zero fast enough so that the sum is finite? Here we have a polynomial in the numerator and a factorial in the denominator. And it is going to be true that factorials really dust polynomials. So factorial is like we've had these races that we've done so far, where we've had the slowest, we had logs, and then we had next were polynomials, exponentials were the fastest. Well, factorials beat them all. So factorials, when we add factorials into the mix for racing, they are amongst these different function classes we were racing against each other. They're going to be our new champion, and we'll see an example of why. But this effectively illustrates the race of the factorial versus the polynomial, because these terms will in fact race to zero fast enough for this to converge, which means the factorial will be dusting the polynomial in the numerator. That being said, the way we show this is with the ratio test. And with the ratio test, factorials are often factorials often lend a series to the ratio test being effective. So, we apply it, and so remember, rho is the limit as n goes to infinity of the n plus first term over the nth term. And this is an example where you have to be quite careful, because it can be really easy to make a mistake. I prefer to not simplify at all in the first step so that you know you get it right. So remember, for the numerator, for the n plus first term, we replaced each instance of n by n plus 1. So we're going to have n plus 1 plus 1, then n plus 2 plus 2 over n plus 1 factorial. So that gives us the numerator. Again, all we did here was just replace each instance of n by n plus 1. For the denominator, we can just copy that nth term. N plus 1, n plus 2 over n factorial. And you can see with the ratio test, it can be very easy to make an algebraic mistake. This is why you have to be very careful. Okay. Let's simplify this. We have here, this is n plus 2. Sorry, I made a mistake here. This should have been n plus 1. So this first term is n plus 2, and then the second term is n plus 3. And we have that n plus 1 factorial in the bottom. Now for the denominator, so this division, division, division by n factorial will put the n factorial up here in the numerator. And this division by n plus 1 times n plus 2, we'll keep that down here. And now we start simplifying. And we see some things cancel. The n plus 2 terms go. And then the question becomes how to deal with factorials. And the secret here is to realize that you can pop terms off of a factorial. So if we kind of just do a little aside here, think about, say, 5 factorial. That's 5 times 4 times 3 times 2 times 1. But note here that what you have, you could write this as a 4 factorial. So you could write this as 5 times 4 factorial. So the idea is, anytime you have a factorial, you can pop terms off of the top. So what we do with this n plus 1 factorial is recognize that that's equal to n plus 1 times n minus 1, all the way down to 3 times 2 times 1. And we're going to pop that n plus 1 term off and lump the rest into n factorial. That allows us to say this is the limit as n goes to infinity of n plus 3 times n factorial. We do that trick here. This n plus 1 factorial we rewrite as n plus 1 times n factorial. And then we still have that other n plus 1. And you see here what happens. The n factorial terms now vanish. And what remains is the limit as n goes to infinity of n plus 3 over n plus 1 times n plus 1, or n squared plus 2n plus 1. Dividing every term, top and bottom, by the dominant term in the denominator, which of course is n squared, gives us n over n squared plus 3 over n squared over n squared over n squared plus 2n over n squared plus 1 over n squared. And we can see this is the limit as n goes to infinity. In the numerator we have 1 over n plus 3 over n squared, and in the denominator we have 1 plus 2 over n plus 1 over n squared. The denominator, when you apply your limit laws, approaches 1. In the numerator, both terms go to 0. So this is 0. If you put all of this together, remember, this was the rho that we just calculated. So rho equals 0, which is less than 1, which means our series converges by the ratio test. And if you think about what the ratio test means, remember what we said before when we gave the test. For large n, the n plus first term is approximately rho times the previous term. What we've just shown in this example is that for large n, the n plus first term is approximately 0 times the previous term. That means these terms are going to 0 really fast, which is confirmation that the factorial really, really dusts the polynomial in their competitive race to infinity. Remember, top is going to infinity, bottom is going to infinity. But this result tells us the bottom is going to infinity dramatically faster than the top. That's just to help think about what's going on. The key thing to understand here is we have shown, because we've gotten a rho of 0, which is less than 1, that this series does converge by the ratio test. Okay. Let's do another example. Looking at this is kind of a complicated example, so it's tough to tell. There's a lot going on here. We have a factorial in the numerator and a factorial in the denominator. There's going to be some leftovers in the numerator, resulting in a polynomial in the numerator when we do some canceling, and an exponential in the denominator. So when you boil this down, this is really polynomial on the top versus exponential on the bottom. And actually, that means we know the exponential will win dramatically over the polynomial. which should result in this being a convergent series. Again, a tricky one to look at and get that sense, but we always like to think about what happens if we can get some insight on the problem before we dive in. Okay, so using the ratio test, we set up our row, limit n goes to infinity. Remember, n plus first term over the nth term. And you have to be very careful with these questions because as you just seeing this, it's going to be complicated. So remember, for the numerator in this ratio test, we replace every instance of n in the summand with n plus 1, and do so very carefully. So first we have n plus 1 plus 3 factorial over 3 factorial n plus 1 factorial and 3 to the n plus 1. So again, that was just going in here and taking each instance of n and replacing it with n plus 1. For the denominator, we just use that nth term as written, n plus 3 factorial over 3 factorial times n factorial times 3 to the n. And now we start to go through and simplify. So this is the limit as n goes to infinity. In this numerator term, we now have n plus 1 plus 3. So that gives us an n plus 4 factorial. Then we still have 3 factorial, n plus 1 factorial, 3 to the n plus 1. And then dividing by this blue term is the same as multiplying by its reciprocal. So we can write that as 3 factorial times n factorial times 3 to the n over n plus 3 factorial. And now start canceling. So the 3 factorials go. But now we see we've got a few things to deal with. We have a few factorial terms, and it looks like this n factorial and this n plus 1 factorial kind of can pair up, and the same with this n plus 4 factorial and n plus 3 factorial. The catch is that we have to pop off some terms. If we want to match up the n plus 4 factorial and the n plus 3 factorial, we need to pop one term off of this n plus 4 factorial term. So we can rewrite that as n plus 4 times n plus 3 factorial. For this n plus 1 factorial to match up with this n factorial, we better pop one term off. So we write that as n plus 1 times n factorial. And then the 3 to the n plus 1 and the 3 to the n, if we rewrite 3 to the n plus 1 as 3 to the n times 3 to the 1, we'll get what we want. Our terms in blue have not changed. We have n factorial 3 to the n over n plus 3 factorial. And now you see a bunch of things cancel. The 3 to the n's go, but also the n plus 3 factorials go, and the n factorials go. And all that remains, limit n goes to infinity, and n plus 4 survives in the top, and n plus 1 survives in the bottom, and the 3 to the 1 term also survives. So this is, we can bring that 3 out front. This is 1/3 times the limit as n goes to infinity of n plus 4 over n plus 1. And we know that limit will be 1. We, again, divide top and bottom, all terms, by the highest power of n in the denominator, which is n. So n over n plus 4 over n over n plus 1 over n, which is 1/3 times the limit as n goes to infinity of 1 plus 4 over n over 1 plus 1 over n. Applying our limit laws, the terms involving n approach 0, and so the limit is 1/3 times 1, or 1/3. And remember, this was a calculation for the row for our ratio test. This is less than 1, which means our series converges by the ratio test. And remember, intuitively, this means as you go further and further down the line of the terms in this sum, the terms look closer and closer, like 1/3. Each term looks closer and closer to 1/3 times the previous term. And so, yes, we conclude that this original series is converging by the ratio test.